So today we're going to be solving the Feb March 2022 paper, right? That's variant 42. There's only one variant in Feb March. Okay, and this is the most recent paper, and this will be following a format similar to what you're going to expect in your 2022 exams, right? This is the format for the new syllabus. All right. So what we have over here is we start with question number 1. Iodine is found naturally in compounds in many different oxidation states. Iodide ions react with acidified H2O2, that's hydrogen peroxide, to form iodine and water. This reaction mixture is shaken with cyclohexane to extract the iodine. Cyclohexane is immiscible with water. Identify the role of H2O2 in its reaction with iodide ions in acidic conditions and write an ionic equation for the reaction. So what's the role of hydrogen peroxide over here? Iodide ions are being converted into iodine. So what's hydrogen peroxide doing? The oxidation state of iodide is going from -1, right, to iodine, that's 0. So that means that iodine is being oxidized. So hydrogen peroxide is acting as an oxidizing agent. Okay. And if you had to write an ionic equation for this reaction, okay, what we have is we have iodide reacting with hydrogen peroxide, okay, in acidic conditions, so that would be H plus, okay, to form iodine and water. Okay, and now we have to balance this equation over here. So what we have is, on the right hand side we have 2 iodines, so let's just first balance the iodides over here. And then what we have is we have 2 oxygens here, so we're going to have 2 H2O over here, and then we have 4 hydrogens on the right, so therefore we're going to need 4 hydrogens on the left. So what we're going to have over here is we're going to balance the H pluses over here, so that's going to be 2H plus, and that's the balanced equation. 15 centimeter cube of C6H12, the cyclohexane over here, right, mentioned in the first part, is shaken with 20 cm cube of an aqueous solution containing iodine until no further change is seen. It is found that 0.39 grams of iodine is extracted into the cyclohexane. The partition coefficient between cyclohexane and water is 93.8. Calculate the mass of iodine that remains in the aqueous layer. Show your working. All right, so what we have over here is we have an initial amount of iodine, okay, which we don't know how much we have. We don't know how much iodine we have initially, okay. So let's say that initially I had X grams of iodine. They've also said over here that 0.39 grams of iodine is extracted into the cyclohexane, okay. So what they're saying is that the iodine that we have in the cyclohexane, that's the organic layer, okay, is 0.390 grams. So let's say initially I had X grams, okay, and in the organic layer after extraction I have 0.390. So then how much is left in the water, right? In the aqueous layer, how much iodine do we have? We have X minus 0.390, right? Because we started with X and 0.39 was extracted into the organic layer. So the remaining is left in the aqueous layer. And now they're saying that the partition coefficient, right, between the cyclohexane, okay, between the cyclohexane and water is 93.8. So what we can say over here is that the concentration of iodine in the organic layer, right, is, we can just take mass per unit volume. It doesn't matter as long as the units are the same in the numerator and the denominator, right, because in partition coefficient the units will cancel each other out. What we have is we have 0.39 grams in 15 centimeter cube of cyclohexane. So we have 0.390 divided by 15, okay, divided by, we have X minus 0.390 in 20 cm cube of aqueous solution remaining. So that's the concentration in the water, and the ratio between the concentrations is the partition coefficient. So this is equal to 93.8. So here if you do your working, what we get is we get 93.8 times X minus 0.390 divided by 20, okay, is equal to 0.390 divided by 15. So here we get X is equal to 0.39554 grams. Okay, so that was the initial amount of iodine that you started with. So in the aqueous layer, you have this initial amount minus 0.390 left. So you minus 0.390, okay, and what you get is you get 0.00554 grams. So that's the amount of iodine left in the aqueous layer over here, okay, or you can say 5.54 times 10 to the power of negative 3 grams. Now over here, okay, what we did was we said that we were doing an extraction, okay. They told we had iodine in the aqueous solution, we had a certain amount, okay, and they said that 0.39 grams was extracted, okay, into the organic layer. So obviously if the initial amount was x, then x minus 0.39 was left in the aqueous layer. The ratio of the concentrations of cyclohexane to water between cyclohexane and water, that is cyclohexane divided by water, that's the partition coefficient, the ratio of the concentrations is 93.8. So we took the concentrations by taking the masses and dividing by the volume. From that we were able to figure out x, okay, and then if we do that, what we get is x is this amount, 0.39554 gram. That was the initial amount. So left in the aqueous layer was just that minus 0.390. Okay. Alternatively, you could have also, what you could also have done is you could have said, okay, in the organic layer we have this much, in the organic layer we have this much, whereas in the aqueous layer, let's say you just have y grams. Okay. And again, if you just solve for y over here, okay, rather than saying x minus 0.390, you could have just taken y. Okay, you could have directly calculated the amount of, or the mass of iodine in the aqueous layer. You could have directly calculated, or you could have just calculated the initial amount and then subtracted how much was extracted. Okay, both methods would be acceptable here. All right, when you're doing your calculations, make sure you just take the calculator value. Okay, make sure you just take the calculator value over here for the final step. All right. Suggest how the value of the Kpc of iodine between hexane 2-on and water compares to the value given in A part 2. Explain your answer. So now they're saying instead of cyclohexane, if I was using hexane 2-on, right, would iodine be more soluble in hexane 2-on or less soluble? Remember, iodine is non-polar, okay, and cyclohexane is also non-polar. So if you're using a polar solvent, hexane 2-on has a dipole, right? It has a dipole. It has a dipole like this, right? Would iodine be more soluble in a polar solvent or in the non-polar solvent? We know that iodine, because it's non-polar, would be more soluble in cyclohexane. So now that the organic layer that we're using is slightly more polar, iodine would be less soluble. So then if the concentration on the organic layer is now lesser, what will happen to the Kpc? If the numerator is now smaller, what will happen to the Kpc? The Kpc would, or the partition coefficient would decrease, right? So we can say over here that the Kpc, okay, the Kpc would be smaller, okay, or would be lower, because hexane 2-on is more polar than cyclohexane, okay, and iodine is non-polar, okay. So we can say that hexane 2-on is more polar than cyclohexane, okay, and because an iodine is non-polar, okay, hence it is more soluble in cyclohexane, or we can say it is less soluble in hexane 2-on. All right, moving on. The group 1 iodides all form stable ionic lattices and are soluble in water. Define enthalpy change of solution. Okay, what is the enthalpy change of solution? The enthalpy change of the solution is the enthalpy change when 1 mole, okay, of a solute dissolves, okay, in excess water, okay, to form an infinitely dilute solution. Okay, 1 mole of a solute dissolves in water, okay, you have sufficiently excess water to form an infinitely dilute solution. It has to be a very dilute solution, okay. So we just say infinitely dilute solution. It's a theoretical thing. Obviously we can't actually have an infinitely dilute solution. It just means that we're using a very large excess of water to measure this enthalpy change, okay. Use the data in table 1.1 to calculate the enthalpy change of solution of potassium iodide. So, what they've given us in this table is, they've given us the enthalpy change when a solid lattice is formed from its constituent gaseous ions, right? So what we have is, we have gaseous ions here, okay? And they've said that if you go down to the solid lattice, okay, that's the lattice enthalpy over here, right? So this lattice enthalpy is equal to negative 629. Okay, this is the lattice enthalpy when 1 mole of a solid is formed from its constituent gaseous ions. Okay, so we have the lattice enthalpy here. They've also said that if you convert the gaseous ions into aqueous ions, okay, if you convert the gaseous ions into aqueous ions, right, what you have is, you have hydration of potassium ions and you have hydration of iodide ions, okay? And that enthalpy change is 322 minus 293. Now negative 322 minus 293. So if you go from gaseous ions, okay, if you go from gaseous ions to aqueous ions, go from gaseous ions to aqueous ions, your enthalpy change, right? Gaseous to aqueous is enthalpy change of hydration. That's the enthalpy change when 1 mole of gaseous ions are dissolved, okay, to form an infinitely dilute solution. Then what you have is, you have negative 322 for potassium, okay, and you have minus 293 for iodide. And obviously what we have to find is the enthalpy change of solution. What we have to find is the enthalpy change of solution, which is when you go from solid to aqueous. So what do we have here? What we can say is that I can convert gaseous ions to solid, and then I can go from solid to aqueous, or I can go directly from gaseous to aqueous. So I can say over here that negative 629 plus x is equal to minus 322 minus 293. So what does x come out to? X comes out to positive 14 kilojoules per mole. Okay. Another thing to remember over here, guys, is this. Another thing that you want to keep in mind over here is this, that if whenever you want to calculate the delta H solution, okay, in this case that they're not asking you to draw a Hess cycle, so you should know that the delta H solution is simply the enthalpy of hydration minus the enthalpy or the lattice enthalpy. Okay, so if you just add up the hydration enthalpies, that's minus 322 minus 293, and you subtract the lattice enthalpies, so that'll be minus 629, you'll get the enthalpy change of solution. So this is a formula that you can also keep in mind, okay, for your calculations. So here the enthalpy change of solution comes out to positive 14 kilojoules per mole. Suggest the trend in the magnitude of the lattice energies of the group 1 iodides, lithium iodide, sodium iodide, and potassium iodide, as you go down the group. So here, if you go down the group, right, the cations become larger. And if you guys remember, the charges are the same. They're all 1 plus ions and 1 minus ions, right? But, and the anion is the same. It's just the cation that's changing over here. And we know that the two things that affect lattice enthalpy are, right, the charge, which is the same, and the size. And we know the larger the cation or the larger the ions, the less exothermic the lattice enthalpy. So over here, we can say that down the group, okay, down the group, the lattice enthalpy will become less exothermic. Okay, so we can say delta H lattice becomes less exothermic. Okay, and the reason why is because the ionic radius increases. So obviously, therefore, charge density decreases, right? Because it's the same charge. It's the same charge. So charge density decreases. Hence we have weaker electrostatic forces of attraction. Okay. Hence, the electrostatic forces of attraction between the ions becomes weaker. Or we can say the ionic bonds become weaker. Forces, okay, of attraction become weaker. Between the ions become weaker. Okay. All right. The concentration of copper 2 plus in a solution can be determined by the reaction of copper 2 plus ions with iodide ions. So here copper 2 plus ions are reacting with iodide ions to form copper 1 iodide, okay, and iodine. The iodine produced in this reaction is titrated against a solution containing thiosulfate ions using a suitable indicator. A 25 cm cube portion of the Cu2 plus solution reacts with an excess of iodide. Okay, so in the first part, we have 25 cm cube of this solution. The end point of the titration occurs when 22.3 centimeter cube of 0.15 mole per dm cube S2O32 minus is added. Calculate the concentration of Cu2 plus in the original solution. So in the what we were using was we were using a 25 cm cube solution of this Cu2 plus, okay, with iodide to form iodine. So in the first part, we were using the copper 2 plus solution, okay, to react with iodide and form iodine. Here, copper 2 plus was acting as an oxidizing agent, and iodide was acting as a reducing agent. This iodine that we produced reacted with the thiosulfate, okay, in the second reaction, and they've given us information for the second reaction here. So what's the first thing you would do here? Based on the information given to you? So here they've given us information about the thiosulfate ion. So we can figure out how much thiosulfate we have, right? We can figure out the number of moles of thiosulfate, okay? We can figure out the number of moles of thiosulfate. That's just the concentration times the volume, which is 0.15 times 22.3 centimeter cube. So that we divide by 1000 decimeter cube. So how many moles did we have of thiosulfate ions in this reaction? So we get 3.345 times 10 to the power of negative 3 moles. And can I say that the number of moles of iodine that reacted in the second reaction will be half as many moles? Because for every 2 moles of thiosulfate, right, we have 1 mole of iodine reacting. So I can say number of moles of iodine is just 3.345 times 10 to the power of negative 3 divided by 2, right? And this is equal to, and then we can say over here, okay, once we have this, we can say over here that the number of moles of copper 2 plus that we have to calculate, the number of moles of copper 2 plus in the initial solution, right, is equal to 2 times the number of moles of iodine, because for every 2 moles of copper 2 plus 1 mole of iodine is produced. So if we just multiply this by 2, if we multiply this value by 2, we get back the number of moles of thiosulfate. Essentially, for every mole of copper 2 plus that reacts, we need 1 mole of thiosulfate, right? So we can say over here the number of moles of copper 2 plus is just the number of moles of iodine times 2. So that will be 3.345 times 10 to the power of negative 3 moles. Okay. And now we have to figure out the concentration of this solution. We have to figure out the concentration of the copper 2 plus solution. So we can say that the number of moles is equal to concentration times volume. And what we have is we have 3.345 times 10 to the power of negative 3 moles of copper 2 plus. This is equal to the concentration times the volume given to us as 25 cm cube of the solution that we used. So that's 25 divided by 1000. So then what is the concentration of the copper 2 plus solution? The concentration comes out to 0.134 moles per decimeter cube. Okay, so that's your answer here. The concentration is 0.134. Identify a suitable indicator for this titration. A suitable indicator for this titration, okay, when iodine is present is starch. Okay, for the thiosulfate iodine titration, okay, a suitable indicator is starch. If iodine is present in solution, okay, then have a blue-black solution with starch. And when the iodine reacts, okay, when the iodine reacts over here, you no longer have that blue-black color. Okay, so the color changes. All right. Copper 1 and copper 2 both contain electrons in all 5 3D orbitals. Sketch the shape of a 3D XY orbital on the axes provided. A 3D XY orbital would be between the X and Y axes. So between the X and Y axes would mean, right, you have one lobe like this, and then you have, right, these are the two axes, this one and this one. So the other lobe will be like this, okay. Obviously this is in 2 dimensions, so you can't really draw it as clearly as you'd like, but this is acceptable. Okay, you just have to show this double lobe over here like that. Okay, make sure you show it between the X and Y axes, which is these two axes here and then these two axes over here. Okay, all right. The reaction of iodide ions with persulfate ions can be catalyzed by Fe3 plus ions. write equations to show how Fe3 plus catalyzes this reaction. Now, this particular series of reaction, when iron 3 catalyzes this reaction, you're expected to know. But if you don't remember, you should know that iron 3 is the oxidized form of iron. So in the first stage, the iron 3 will take the electron from whatever is undergoing oxidation. So here iodide is undergoing oxidation. So in the first stage, okay, the iron 3 plus will react with the iodide. It will react with the iodide, okay, to form Fe2 plus, okay, and iodine. Right? And if you have to balance this equation over here, what will happen is that for every 2 iodides, you're going to need 2 Fe3 pluses. Here what's happening is that, right, each Fe3 plus is gaining an electron and each iodide is losing an electron. So you're going to need, for 2 iodides over here, when you balance it with the iodine, you're going to need 2 Fe3 pluses. And the second stage, okay, the Fe2 plus, in the second stage, the Fe2 plus will react with the S2O8 2 minus, okay, to form sulfate ions, okay, and regenerate the Fe3 plus ions. So we can clearly see over here that the iron 3 is acting as a catalyst. And if we balance the second equation over here, what do we have? Over here, what we have is, from the first part, we have 2 of these, okay, and we have 2 of these being regenerated, and obviously we're going to have 2 sulfate ions here as well. Okay, so that's the balanced equation. An orange precipitate of HgI2 forms when Hg2 plus ions are added to CAIE aqueous. The solubility of HgI2, that's mercury iodide, mercury 2 iodide, at 25 degrees Celsius is 1 into 10 to the power of negative 7 grams per decimeter cube. Calculate the solubility product of HgI2. Include units in your answer. They've given us the MR of HgI2. Okay, that is 454.4. So first, let's actually convert the grams per decimeter cube into moles per decimeter cube. Okay, so we have 1 into 10 to the power of negative 7 grams per decimeter cube. So we can say over here that the number of moles is equal to mass divided by the molar mass. That is 10 to the power of negative 7 divided by 454.4. Okay, so how many moles does that come out to per decimeter cube? So what we get is, we get 2.20 times 10 to the power of negative 10 moles. Okay, so the solubility in moles per dm cube, okay, the solubility in moles per dm cube is 2.20 times 10 to the power of negative 10 moles per decimeter cube. Okay, now we have to figure out the solubility product of HgI2. So let's just write down the equilibrium over here, right? We have HgI2 dissolving to form Hg2 plus 2 iodide minus. Now over here, okay, we had a certain amount of mercury 2 iodide to begin with. Okay, we don't know how much we had, but what we do know for a fact is that the solubility is 2.20 times 10 to the power of negative 10 moles per decimeter cube, right? So initially we had a certain amount, and okay, let's say that we had X moles initially. We don't really care about how much we had initially, okay, when we formed the mercury iodide over here. But we know at equilibrium, okay, okay, per decimeter cube minus 2.20 times 10 to the power of negative 10 moles per decimeter cube dissolved. Okay, so can I say that this is how many moles of mercury 2 plus ions were formed, right? Because we have a 1:1 ratio here, and over here I can say that I had 4.40 times 10 to the power of negative 10 moles per decimeter cube of iodide ions forming over here. So at equilibrium, we don't really care about the HgI2 concentration, that's just X minus this. But we know that these are equilibrium concentrations for mercury and iodide. At equilibrium, we have 2.20 times 10 to the power of negative 10 moles per decimeter cube of mercury ions, and we have 4.40 times 10 to the power of negative 10 moles per decimeter cube of iodide ions. And if we look at the KSP, right, the KSP over here is equal to the concentration of Hg2 plus times the concentration of iodide squared, right, which is 2.20 times 10 to the power of negative 10 multiplied by 4.40 times 10 to the power of negative 10 squared. So what does the KSP come out to? So here we get 4.26 times 10 to the power of negative 29. Okay, so the value of KSP is 4.26 times 10 to the power of negative 29, and the units are concentration cube. Okay, the units over here are, we have concentration times concentration squared, right? So the units will be concentration cube, which is mole cube, okay, mole cube dm to the power of -9. Okay, now again, what I want you guys to understand is this. Okay, we had a certain amount, let's just assume we had 1 decimeter cube of solution. Okay, initially they said that this is how much of the mercury iodide dissolved. Okay, 1 into 10 to the power of -7 grams in that 1 decimeter cube. So we can figure out, okay, we had a certain starting amount of the solid, we had 0 moles of the ions. Okay, and at equilibrium what happened was 2.20 times 10 to the power of -10 moles per decimeter cube dissolved. Okay, therefore the same number of moles of mercury ions were formed in solution because we have a 1:1 ratio, and twice the number of iodide ions were formed in solution because that's a 2:1 ratio. So we figured out the equilibrium concentrations because we had initial was 0 and we know this much was formed. So we just add these two and we get the equilibrium amounts for the ions, right? Which the product of these raised to their stoichiometric coefficients give us the KSP. Okay. Here I represents the initial amount, C represents the change in the concentration, and E represents the equilibrium amounts. We don't care about the equilibrium amount of the solid because the solid doesn't show up in the equilibrium expression. Okay. Here we have question number 2, which says silicon is the second most abundant element by mass in the Earth's crust. In industry, silicon is extracted from SiO2 by reaction with carbon at over 2000 degrees Celsius. Explain why the entropy change of this reaction is positive. So why do we have an increase in entropy in this reaction? Because we have more moles of gas on the right? There's no gas on the left, but we're forming gas on the right hand side. Also, what we're also doing is we're forming liquid from solid, right? So gas and liquid will have more entropy than the solids. So we can say over here that 3 moles of solid, okay, 3 moles of solid are converted into 1 mole of liquid, okay, and 2 moles of gas, which have higher entropy. So you have a positive entropy change. Okay. Reaction 1 is highly endothermic. Suggest the effect of an increase in temperature on the feasibility of this reaction. Explain your answer. So when we're talking about feasibility, right, what we have is we have delta G is equal to delta H minus T delta S. Okay. Now, in order to increase the feasibility, we want delta G to become more negative. Okay. Now, what this is saying over here is this, that the delta H is positive. Okay, the delta H is positive. So we can say that delta G is equal to some positive value for the delta H. Okay. And then we have minus the temperature times delta S, and delta S is also positive over here. Delta S is also positive over here. So what happens if I increase the temperature? What happens if I increase the temperature? Now over here, what we can say is that if I increase the temperature, right, this entire term becomes more negative. This T delta S term, right, this minus T delta S term becomes more negative because T is always positive, the entropy change is positive, so T delta S is positive. So minus T delta S is negative. Increase the temperature, this becomes more negative, therefore delta G becomes more negative. So we can say that if I increase the temperature, okay, the feasibility increases. Okay. And the reason why, okay, and they want you to explain it in terms of the equation for delta G. The reason why is because over here T delta S is positive, okay, therefore minus T delta S is negative, okay, is negative. And if you increase the temperature, okay, and increasing the temperature results in minus T delta S, and therefore delta G becoming more negative. All right. Silicon is purified by first heating it in a stream of HCl to form SiHCl3. The SiHCl3 formed is then distilled to remove other impurities. Table 2.1 shows some standard entropy data. Use the data in table 2.1 to calculate the standard entropy change for reaction 2. So, What is the standard entropy change for a reaction? It is simply the standard entropies of the products minus the standard entropies of the reactants. Okay. Now, if you look at the products here, we have Si8Cl3 and hydrogen gas. So the standard entropies, we have 1 mole of each, right? So Si8Cl3 has a standard entropy of 314. Okay. Hydrogen gas has a standard entropy of 131. And then we minus the standard entropies of the reactants. We have 3 moles of HCl, so that will be 3 times 187 minus 3 times 187. And then we also subtract the entropy of silicon, which is minus 9, which is, we subtract 19 over here. And that gives us the standard entropy change as negative 135 joules per Kelvin per mole, right? So the units for entropy. So that's our answer. All right. Reaction 3 is the reverse of reaction 2 and is used to obtain pure silicon. Use this information and your answer to B part 1 to calculate the temperature in Kelvin at which reaction 3 becomes feasible. Show your working. So what is the temperature at which the reaction becomes feasible, right? The reaction is feasible when the Gibbs free energy change is less than 0, right? So we want to calculate the temperature at which the Gibbs free energy change is equal to 0. We want to figure out the temperature, okay, at which the Gibbs free energy change is equal to 0. So we can say over here that delta G is equal to delta H minus T delta S. Okay. They've given us the enthalpy change for this reaction. The enthalpy change is 219.3 kilojoules per mole. The temperature is what we have to figure out. And the entropy change for this reaction, okay, this is the backward reaction. So in the previous part, we had an entropy change of negative 135 joules per Kelvin per mole, right? That was this reaction from products to reactants. So this reaction over here, as it's shown, will have an entropy change of positive 135 joules per Kelvin per mole, right? So we have 135 plus 135 joules per Kelvin per mole. So convert that to kilojoules. We divide by 1000, okay? And this is equal to 0. This is equal to 0, okay? So what we get over here is we get 0.135 T is equal to 219.3. Okay, so what is the temperature equal to? This comes out to 1624 Kelvin. Okay, so what that means over here is at 1624 Kelvin, okay, the delta G is equal to 0. Above that temperature, the delta G will be negative, the reaction will be feasible. Below that temperature, the reaction will be infeasible. Okay, so here we have 1624 Kelvin. Silicon can also be produced by the electrolysis of SiO2 dissolved in molten calcium chloride. The relevant half equation for the cathode is shown. Calculate the time in seconds required to produce 1 gram of silicon by this electrolysis using a current of 6 amperes. Assume no other substances are produced at the cathode. So here they've given us the reaction at the cathode, okay, and they've said we want to produce 1 gram of silicon, okay, and they want to know how many seconds do I need to pass a current for, okay, in order to produce this 1 gram of silicon. Now the first thing we need to do over here is we need to figure out the number of moles of silicon. Okay, from that we'll be able to figure out the number of moles of electrons, and from the number of moles of electrons, right, we'll know how much charge we need to pass, and from the charge we can figure out the time. Okay, that's what we're going to do. So what we have is number of moles of silicon is the mass divided by the molar mass, that's just the relative atomic mass here. So that'll be 1 divided by 28.1, right? So what do we get for the number of moles of silicon that we're trying to produce here? So we get 0.03559 moles. Okay, so then I can say that the number of moles of electrons over here, is simply 4 times the number of moles of silicon, right? Because we have a 4:1 ratio. So what we have is number of moles of electron is 4 times the number of moles of silicon, and this is equal to, this comes out to 0.142 moles. All right, so we have 0.142 moles of electrons. Now we know that 1 mole of electrons, okay, has a charge of 96,500 coulombs. So then we can say that if we have 0.142 moles of electrons, right, we have 0.142 moles of electrons, that will have a charge of, let's say, q coulombs. Okay, this is the idea over here, is that we have q is equal to nf. Okay, q is equal to nf, where n is the number of moles of electrons and f is just Faraday's constant, right? And that's 96,500 coulombs per mole. So then what is the charge over here? So here we get charge is equal to 13,736 coulombs, right? That's 0.142 times 96,500. And this q, okay, this q is equal to the product of the current and the time in seconds. Okay, that's what we have to figure out. We have to figure out the time. The current that we have is 6 amperes and the time is just t. Okay, and this is equal to 13736. So what does t come out to? If you just divide this value by 6, what we get is 2,289 seconds. Okay, we get 2,289 seconds. So that's your answer. All right. So here we have question number 3. It says titanium is a transition element in period 4. It is commonly found as TiO2 in minerals. Define transition element. Okay, it is an element. It is an element that forms at least one stable ion. Okay, at least one stable ion with a partially filled d subshell. Again, this definition is the definition that they want in Cambridge. Okay, it is not the actual definition of a transition element, but this is the one they want for your A-level exam. Okay, for the CAIE exam. So we can say partially filled d subshell, or we can say partially filled d orbitals. Identify two properties of transition elements. Okay, two properties, they could be chemical or physical properties. Okay, so one property that they have is that they have variable oxidation numbers, okay, or variable oxidation states. Another property that they have is that they form colored solutions. Okay, they form colored solutions or colored complexes. Okay, they also act as catalysts, right? Homogeneous catalysts, heterogeneous catalysts, etc. They can also form complex ions and so on. Okay, so there are multiple properties, but these are just two of the properties that we have. The TiO2 plus ion forms when TiO2 reacts with an excess of sulfuric acid. TiO2 plus can be reduced by zinc metal in acidic conditions to form a purple solution containing Ti3 plus. TiO2 plus is a colorless ion. Suggest why. Now, if you look at the periodic table, okay, the titanium atom, okay, its configuration is argon, 3d2, 4s2. Okay, and in this TiO2 plus over here, right, titanium has an oxidation number of +4, because obviously oxygen is -2, so 4 minus 2 gives you 2 plus, right? So over here we know that titanium has an oxidation number of +4, so that means that Ti4 plus, okay, Ti4 plus over here, okay, if you look at the configuration of Ti4 plus, it has the same configuration as argon. It's lost its s2 electrons and it's lost its 3d electrons. So can we say that it doesn't show color because there are no electrons present in the d subshell? Okay, there are no electrons present in the 3d subshell over here, right? We have 3d 0 over here and 4s 0 obviously. So we can say over here that Ti4 plus, okay, Ti4 plus has no electrons, okay, has no electrons in the d subshell. Okay, so therefore obviously there can't be any, you can't have that absorption of UV light that promotes an electron. Okay, so here we can say hence, okay, it does not absorb visible light, to promote an electron. Okay, to promote an electron from the lower energy d orbital to the higher energy d orbital, because there are no electrons in the d orbitals. Give the electronic configuration of an isolated Ti3 plus ion. 3 plus would be, you would lose the 4s2 and then you would lose one of the 3ds over here. So this would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d1, right? You've lost that 4s2 and one of the d electrons over here. Write an ionic equation for the reduction of TiO2 plus by zinc metal in acidic conditions. Again, what we have is we have zinc, reacting with TiO2 plus in the presence of acid, so that will be H plus, to form Ti3 plus. Okay, the question is given as that we're forming Ti3 plus. Okay, and obviously we're also going to form zinc. And what else do you think we're going to form over here? We have hydrogen and oxygen left to balance over here, so we're going to form H2O. Now titanium, okay, over here is going from +4 to +3, and zinc, because it's a reducing agent, right, it'll form the cation, it'll lose electrons, forms Zn2 plus. That's the only ion that zinc forms. Okay, so that means if titanium is going from +4 to +3, it's changing by -1, whereas zinc is going from 0 to +2, right? So the change in zinc over here, the change for zinc is +2, the change for titanium is -1. So that means we're going to need 2 titaniums for every 1 zinc. So we're going to need 2 titaniums, okay, for every 1 zinc over here. All right, because we're going to need 2 of these, okay, to balance the increase in oxidation number of zinc. So that means if we just balance the H pluses at the end, right, what we have over here is we have 2 oxygens on the left hand side, so we're going to need 2 oxygens on the right, so that'll be 2H2O, and then we have 4 hydrogens, so we're going to need 4H plus. Okay, so this is the balanced equation. Acidified Ti3 plus aqueous, okay, that's this guy, reacts with oxygen dissolved in water as shown. Okay, the standard Gibbs free energy change is negative 436.1 kilojoules per mole. The standard reduction potential of oxygen, right, reacting in acidic conditions, okay, gaining electrons to form water, is plus 1.23 volts. Calculate the standard reduction potential in volts of the TiO2 plus Ti3 plus half cell. Show your working. Now over here, okay, we have to figure out the standard reduction potential of this half cell, right? The half cell where we have Ti3 plus and TiO2 plus. Now, what we know for a fact is that they've given us standard Gibbs free energy change, okay, and this can be used to figure out the E naught of the overall cell. This can be used to figure out the EMF of the cell, okay, and the relationship that we have is that the standard Gibbs free energy change is equal to negative N times F, that's Faraday constant, times the E naught of the cell, okay. Now, N over here represents the number of moles of electrons that are being exchanged. Now, that means over here is that if you look at the overall equation, you have 1 mole of oxygen. And in the half equation they've given us, we also have 1 mole of oxygen. So the half equation is already balanced for us. So what that means is in our reaction, oxygen is gaining 4 electrons, and therefore Ti3 plus, okay, Ti3 plus will be losing 4 moles of electrons. So the number of moles of electrons being exchanged, okay, the number of moles of electrons being exchanged is 4. Faraday's constant is 96,500 coulombs per mole, and the E naught of the cell is what we have to figure out, okay. And the standard Gibbs free energy change over here, okay, we're going to take it in joules, okay, because all of these units will come out to joules per mole. Okay, the standard Gibbs free energy change in joules will be negative 436,100, okay, it will be negative 436,100. So what does the E naught of the cell come out to in this case? The E naught of the cell comes out to 1.13 volts. Okay. So what they're saying over here is this. Okay, what we can say over here is that we had this half equation for this reaction of reduction of oxygen, and then we can say over here, okay, that because oxygen is undergoing reduction, this Ti3 plus over here, okay, this Ti3 plus over here is undergoing, this Ti3 plus over here is obviously undergoing oxidation, right? So the Ti3 plus is undergoing oxidation to form TiO2 plus, and it's losing electrons, right? Now obviously this isn't the balanced equation, but the idea is that we know we can find out the EMF of this half cell. We know, let's call this X. We know that 1.23 plus X gives us 1.13. That's the overall EMF of the cell, right? This half equation plus this half equation gives us the overall EMF. So then what is X equal to? X comes out to negative 0.10 volts. Negative 0.10 volt is the potential for the loss of electrons. So the standard reduction potential, which will be for the gain of electrons, remember, standard reduction potential is if the electrons are on the left hand side, the standard reduction potential here will be plus 0.10 volts. Again, what I did here was I figured out the EMF of the cell, okay, using the relationship that I know between Gibbs free energy change and the EMF, okay. And from the EMF of the cell, I was able to determine the EMF, okay, or the potential for this half equation. Okay, obviously this half equation isn't balanced. I haven't written down the oxygens and everything here, but this is just to show you that Ti3 plus was obviously losing electrons. And here again, I know that if I add up the two reactions, 1.23 plus X, I get the overall potential. So that's negative 0.10 volts, right, is the potential for this half equation. But this half equation is shown for the loss of electrons. The standard reduction potential is for this half cell the gain of electrons. So if this reaction as it's shown is minus 0.10 volts, then the standard reduction potential, where electrons are written on the left hand side, right, it's shown for the reduction reaction, the standard reduction potential will be the reverse of this, which is plus 0.10 volts. When aqueous citrate ions C6H5O7 3- are added to Ti3 plus aqueous, this complex ion is formed. Okay, explain in terms of d orbitals why Ti3 plus is able to form complex ions. The reason why transition element atoms or ions can form dative bonds, okay, or can form complex ions is because they can accept lone pairs of electrons from ligands because they have empty d orbitals. Okay, they can accept. Okay, so over here Ti3 plus can accept okay, lone pairs of electrons okay, from ligands, okay, because it has vacant or empty, because it has vacant d orbitals. It has vacant d orbitals. Okay, because it has empty orbitals, it can accept those lone pairs, and then those ligands can form dative bonds. This acidified complex ion does not react with oxygen dissolved in water, unlike acidified Ti3 plus aqueous. Suggest what this means for the value of the standard reduction potential of the following half cell. So in the previous case, okay, the half cell was just 0.10. Okay, what that meant was that the reverse reaction, okay, the standard reduction potential was 0.10, right? So that meant that Ti3 plus could easily lose electrons, and that would still have an electrode potential of minus 0.1. So 1.23 minus 0.1 would give you a positive value. Plus 1.23 minus 0.1 would give you a positive value. In this particular case, what it means is that the standard reduction potential over here, okay, the standard reduction potential for this half cell, the standard reduction potential, okay, that is the E naught for this particular half cell, okay, is going to be greater than plus 1.23 volts. Okay, the reason why is because, okay, the reason why is because if this value, right, for the second case, if this value was greater than 1.23, then this reaction would be more negative than 1.23. It would be more negative than 1.23, so the overall reaction would give you a negative EMF for the cell. So we can say that the standard reduction potential here must be greater than, okay, it must be greater than 1.23. Okay, must be greater than 1.23 volts. Over here, okay, if you take this half equation, over here that they've given to us, right? Let's just take this half equation over here. Now, what they're saying over here is that if oxygen is acting as the oxidizing agent, it's undergoing reduction. This guy must be being reduced, right? Now, in this particular case, if you look at this reaction, the E, okay, this E must be more negative than 1.23. If it's more negative than 1.23, the overall reaction will still have a negative EMF. Okay, so the standard reduction, if this value over here, okay, is more negative than negative 1.23, right, which means that the overall EMF will be negative. So that means if you look at the standard reduction potential, right, it must be more positive than 0.12 than 1.23. For example, if this was negative 2, then the standard reduction potential would be positive 2. right? Some reactions of TiO2 are shown in figure 3.1. The anion ACAC- is a bidentate ligand. TiO2 reacts with chlorine to form TiCl4, which reacts with this bidentate ligand, okay, which reacts with this bidentate ligand to form this complex here. And TiO2 can also react with fluoride ions to form TiF62-. The titanium ions in TiF6 and in Ti in this complex over here have a coordination number of 6. Explain what is meant by the term coordination number. The coordination number, okay, is the number of coordinate bonds. Okay, it is the number of coordinate bonds or the number of dative bonds, okay, formed to the central metal ion. It is the number of coordinate bonds, okay, or dative covalent bonds formed by the central metal ion, okay, by the central metal atom or ion. All right. Write an equation for the formation of TiF6 from TiO2. So what we have over here is we have TiO2, okay, reacting with 6HF, okay, you have 6 of these guys over here to form TiF6 2 minus, okay, and then what are we left with? We have 6 hydrogens and 2 oxygens. We have 6 hydrogens and 2 oxygens. So that means we're left with, okay, 6 hydrogens and 6 H pluses and 2 oxygens, right? 2 oxides over here. So that means we're left with we're left with 2 H3O plus. Okay, we're left with 2 H3O plus over here. Or you can say over here that you're gonna make 2 H2O plus 2 H plus. Okay, either way is acceptable. Obviously, if it's neutral on the left hand side and you have an anion here, then you have to balance the charges. So you will definitely produce H plus. So either you can say 2H2O plus 2H plus, or you can say 2H3O plus. Okay, they're both acceptable. State what is meant by a term bidentate ligand. Okay, a bidentate ligand is a species that donates, okay, that donates two lone pairs of electrons, okay, to form, two dative bonds, okay, two dative covalent bonds with a central metal atom or ion, bonds with a central metal atom or ion. All right, moving on. This guy over here, this complex ion, okay, this octahedral complex shows both optical and geometrical or cis-trans isomerism. It exists as 3 stereoisomers. The structure of one stereoisomer is shown in figure 3.2. Complete the structures of the other 2 stereoisomers of this complex. Now the cis isomer shows optical isomerism as well, right? This is the cis isomer shown where the 2 chlorides are 90 degrees from each other. So we can draw the optical isomer of this and just draw it the way they've shown it to you. So the way they've shown it is, now here if you took the mirror image of this, what do you get? What do you get over here? What you get is this guy, right? Now it'll be closer to the mirror on the left hand side. So we get this, right? And then we have AC, and then we have, okay, this. So that's this guy over here, right? It's on the left now. Then you have this guy over here, okay? And then the last thing that you have is you have the 2 chlorides over here, right? Here they've shown it on the left hand side, right? So then they're going to be on the right in the mirror image like this. Okay, so this is the optical isomer of the cis form. And then we also have the trans isomer here. In the trans isomer, you can simply say, okay, the 2 chlorides are on opposite sides. The 2 chlorides are on opposite sides over here. So what are we left with? What we're left with over here is this. We have this guy, okay, and then we have this guy. And then we have AC, okay, and then we have AC. Okay, so this is the trans isomer. So this guy is showing geometric isomerism, right? This is the cis isomer, this is the trans isomer, and obviously the cis isomer has a mirror image. Okay, so it shows optical and geometric isomerism. The AC minus ion is symmetrical. Deduce which, if any of the stereoisomers 1, 2, and 3 are polar. Okay, now which of these isomers will be polar? Will it be the cis isomer or the trans isomer? Which one will be polar? Okay, if you look at the trans isomer, what you have is the net dipoles cancel each other out, right? The dipoles, the bond dipoles, the Cl and Cl dipoles cancel each other out. Whereas in the cis form, right, you have a dipole towards the chlorides over here. So we can say over here that the trans isomers, the cis isomers, sorry, are polar. Okay, so isomers 1 and 2, the ones I've drawn are 1 and 2. Okay, are the cis isomers, they are polar. Okay, and the reason they're polar is because they have a net dipole. Okay, because they have a net dipole. Okay. All right, so here we have question number 4. Compounds F and J are shown in figure 4.1. F and J both contain the arene functional group, right? That's this benzene ring over here. Identify the other functional groups in F and in J. In F, we have a carboxylic acid group. Okay, we have a carboxyl group, and we also have a phenylamine group. Okay, don't just say amine, we have a phenylamine group. Okay, so in F, we have phenylamine, okay, and carboxylic acid. And in J, what we have is we have a phenol and we have an ester. Okay, we have a phenol and an ester. So in J, we have a phenol and ester. Okay. State the number of chiral centers in a molecule of F and a molecule of J. Does F have any chiral centers? Unsaturated, all the carbon atoms, and this is also unsaturated. So F has 0 chiral centers. Okay, F has 0 chiral centers. Right? There's no sp3 carbons in F at all. What about J? How many chiral centers does J have? We have a chiral center here, and we have a chiral center over here, right? These are all CH2s, and this carbon is bonded to 2 methyl groups, right? And all the other carbons are sp2 hybridized. So we have 2 chiral centers in J. A student proposes a multi-step synthesis of F from benzene as shown in table 4.1. Complete table 4.1 by providing relevant details of the reagents and conditions for steps 1 and 4 and the structure of product D. Okay, so what we have over here is in the first step, right, this guy, benzene is converted to methylbenzene. So this is electrophilic substitution, right? And this is alkylation, Friedel-Crafts alkylation or alkylation of benzene. So we're going to use CH3Cl, okay, and AlCl3, okay, and we're going to use heat, or we can say warm, okay. In most cases, they also accept it without the warming, but just write it down anyways, okay. In the second part, the methylbenzene is reacted with concentrated nitric acid and concentrated sulfuric acid, okay. And what we see is this is nitration, okay. Now the methyl group is 2,4 directing, so the nitro will either go to the 2 position or the 4 position. But the way they've shown it over here, the nitro must be going to the 4 position, okay. So the product D over here is this guy, okay. You have the methyl group and you have the NO2 going to the 4 position. It can also go to the 2 position, but they've shown here that the methyl goes to the nitro goes to the 4 position here. Okay. In the third step, D is reacted with hot alkaline KMNO4 and then acidified. What that does is it converts the methyl group into a carboxylic acid. Okay. If you use alkaline conditions, you make the salt of the acid. So you make CO2 minus, and then that CO2 minus reacts with more acid to form CO2H. That's why we acidify. Okay. And step 4 over here, what we're doing is we're converting the nitrobenzene group into a phenylamine group. Okay, this is reduction of nitrobenzene to form phenylamine. Okay, and for this you're going to use tin and concentrated HCl, okay, and heat. Okay, this is reduction. The reducing agent over here is tin. Okay, tin is not a catalyst here, it's the reducing agent. Okay. In a second multi-step synthesis, the student changes the order in which the reagents and conditions are used. The reaction scheme is shown in figure 4.2. Okay. In step one, the benzene is converted to methylbenzene. Okay, again you're using CH3Cl and AlCl3 in heat. Then you oxidize the methyl group to a CO2H, and then you nitrate it. So in the previous case, what we did was we did the nitration of the methylbenzene first, and then we oxidize the methylbenzene. In this case, okay, we're oxidizing the methylbenzene first and then nitrating it. Okay, they're saying G over here, okay, is the major product of the synthesis. Okay, and G is going to be an isomer. It's going to be an isomer of E that we produced in the first part. Okay, it's going to be an isomer. But now what's happened is that what's happened over here is this, that rather than E, they're saying why is G the major product rather than E? And the reason, what happens is in G what we have is this. Okay, we have a CO2H. Okay, and where does the nitro group go? The CO2H, is it 4 directing, 2,4 directing, just like the methyl group was, or is it going to direct it in some other direction? The acid group is 3 and 3 directing over here, right? So the NO2 will go on the 3 position. The NO2 will go on the 3 position over here. So G is this guy. Okay, so over here what we can say over here is that, okay, generally speaking, you guys should know this, that generally speaking electron withdrawing groups are 3 directing. Okay, so here we can say that the CO2H group, okay, is an electron withdrawing. Okay, there are some exceptions to this. The only exception that you guys learn about is chlorobenzene. Okay, that's 2,4 directing, but it's also deactivating. But the CO2H group, usually deactivating groups, okay, that make the benzene ring less reactive, are 3 directing. Okay, so it's an electron withdrawing 3 directing group. All right. J reacts under suitable conditions with sodium hydroxide aqueous. After acidification of the reaction mixture, compounds K and L form. Right? Give the molecular formula of L. Now, what type of a reaction is taking place over here when this reacts with NaOH aqueous? What functional group in J will react with sodium hydroxide aqueous? It will be the ester linkage, right? We have ester hydrolysis. So you're gonna form this guy over here, right? This is your gonna be your acid group, right? The salt of this and the salt of the phenol, and then we acidify it to form this, right? We form the acid and the phenol. So this acid group forms here, whereas over here we form the alcohol. So L over here is this guy. Okay, this is L. We have this, and then we have the OH. Okay, we have the OH over here. And what is the molecular formula? You have how many carbon atoms? 1, 2, 3, 4, 5, 6 carbon ring, right? And then you have 7, 8, 9. So what you're going to have for your molecular formula is C9H18O. Okay, because if you had a regular alcohol, it would be C9H20, right? But because you have a ring, it'll be 2 fewer hydrogens. So that is C9H18O. And you can also count the number of carbon and hydrogen atoms here. You have 3 plus 3, that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Okay. The two types of reactions that are occurring when J reacts with NaOH are, you have neutralization taking place, acid-base reaction, right? You have acid-base reaction because you also have a phenol group here, right? That reacts with NaOH aqueous, and you have hydrolysis. So you have hydrolysis, okay, that's breaking the ester linkage, and you have neutralization, or you can say acid-base. K can also be synthesized from phenol. Figure 4.4 shows several reactions of phenol. Okay, in reaction 1, phenol reacts with sodium to form M. Okay, so in reaction 1, sodium reacts with phenol to form M. So we have to write the equation for the formation of M in reaction 1. The formation of M will be C6H5OH reacts with sodium to form a salt and hydrogen gas, right? You guys remember? OH groups react with sodium to form hydrogen gas. Draw N, which is the product of reaction 2. Okay. So in reaction 2, okay, what happens is that phenol reacts with excess bromine aqueous to form 2,4,6-tribromophenol, right? That's your white precipitate, right? And decolorization of aqueous bromine. So in reaction 2, okay, phenol is reacting with aqueous bromine to form 2,4,6-tribromophenol. Okay, this is your white precipitate. And the observation is you see a white precipitate and you see decolorization of aqueous bromine. Explain why phenol is a weaker acid than K. Essentially, the question is asking why are phenols weaker acids than carboxylic acids? Okay, why is phenol a weaker acid than a carboxylic acid? And the reason why is because in the carboxylic acid, okay, in K, okay, we can say the conjugate base of K, okay, the conjugate base of K is more stable than the conjugate base of phenol, that is the phenoxide ion. Okay, it is more stable than the phenoxide ion due to the electron withdrawing, okay, due to the electron withdrawing C double bond O group. Okay, the carboxylic acids have the C double bond O that makes them stronger acids than phenols. Phenol and benzene both react with nitric acid as shown. Okay, explain why the reagents and conditions for these two reactions are different. So why is phenol so much more reactive? Right, with phenol you just need dilute nitric acid, whereas with benzene you need concentrated nitric acid and concentrated sulfuric acid as a catalyst. Right, the reason why is because phenol is much more reactive because, okay, phenol is much more reactive because, okay, phenol is much more reactive than benzene, okay, much more reactive than benzene. Okay, that's why it needs milder conditions, okay, because the lone pair, okay, the lone pair on the oxygen atom, okay, the lone pair on the oxygen atom, okay, is in phenol is delocalized into the benzene ring, okay, is delocalized into the benzene ring, okay, making the benzene ring much. So basically what happens if it delocalizes into the benzene ring, the lone pair goes into the benzene ring, it means that the benzene ring is more electron rich, okay, the benzene ring is more electron rich, so therefore we can say that the electron density in the ring increases, okay, and the ring increases, okay, making the ring more reactive towards electrophile, okay, making it more reactive towards electrophile. So here we have question number 5, which says 2-chloropropanoic acid is used in many chemical syntheses. An equilibrium is set up when CH3Cl, CH3CHCl, COOH is added to water. Write the equation for this equilibrium. So obviously this is a weak acid. So what we have is we have CH3, CHCl, CO2H, okay, reacting with water. Okay, and here obviously the carboxylic acid is a weak acid, so it donates the protons and water will act as the base, right? So what you form is CH3, CH, Cl, CO2 minus and H3O plus. 0.15 moles of this acid, right, 2-chloropropanoic acid, dissolves in 250 cm³ of distilled water to produce a solution of pH 1.51. Calculate the pKa for this acid over here. Okay, now what we have over here is we have this equilibrium, right? We have the equilibrium that we've shown, right? And we know that the Ka is simply the concentration of H plus, or you can say the concentration of H3O plus, okay, times the concentration of the conjugate base, that is CH3, CHCl CO2 minus, okay, divided by the concentration of the acid, divided by the concentration of the acid, right? Now the concentration of H plus at equilibrium is the same as the concentration of the conjugate base, right? If for example X moles of this are forming of H plus, then X moles of this will form. Obviously H2O is not part of the Ka constant. So what we have is, we have the number of moles of the concentration of H plus is 10 to the power of negative pH. So that is 10 to the power of negative 1.51. You guys remember, the concentration of H plus is equal to 10 to the power of negative pH. So that's the concentration of H plus, and we have the same concentration of the conjugate base. So that concentration times the same thing, right? That will be squared, divided by the concentration of acid. What is the concentration of acid? Well, that is, the concentration is number of moles per unit volume for the acid, right? The number of moles is 0.150, right? And the volume is 250 cm cube. So that is 0.25 decimeter cube. So we can say over here that the concentration of the acid is 0.6 moles per decimeter cube. And we know that at equilibrium, we can assume the equilibrium concentration for a weak acid is the same as the initial concentration, right? So this is our Ka. So what does the Ka come out to over here? For the Ka, we get 1.592 times 10 to the power of negative 3 moles per decimeter cube. So then what is the pKa? What is the minus log of Ka, right? That is the pKa. So what's the minus log of this number over here? So the pKa over here comes out to 2.80. Okay. An equal concentration of aqueous propanoic acid has pH 2.55. Explain the difference in pH of the solutions of equal concentration of this and propanoic acid. Now, 2-chloropropanoic acid had a pH of 1.51. Okay, so propanoic acid has a higher pH for the same concentration. So in other words, this acid is a stronger acid than propanoic acid. Why? Why is this acid a stronger acid than propanoic acid? It's because of the electron withdrawing chlorine atom. Remember, more electron withdrawal means a more stable conjugate base, which means a stronger acid. Okay, so what we have over here is, okay, what we can say over here is that 2-chloropropanoic acid, okay, chloropropanoic acid is a stronger acid, than propanoic acid. Okay, because the conjugate base, okay, because the conjugate base is stabilized, okay, the conjugate base is stabilized or is more stable, okay, due to the presence of a electron withdrawing chlorine atom, due to the presence of an electron withdrawing chlorine atom. Okay, electron withdrawing chlorine atom. When CH3CHCl CO2H, that is 2-chloropropanoic acid, reacts with NH3, alanine forms. Alanine is an amino acid. Its isoelectric point is 6.1. State what is meant by the isoelectric point. Okay, the isoelectric point is the pH, okay, at which a molecule, okay, or we can say at which an amino acid, okay, in this case it's an amino acid, at which a molecule has no net charge, or we can say there's a pH at which the molecule is neutral. Okay. Give the structural formula of alanine at pH 2. Now at pH 2, what will happen is, at pH 2, okay, the pH is below the isoelectric point. So at 6.1, it's neutral. Below 6.1, there's more H plus ions. Okay, so this guy over here, the NH2, gains a proton. If the pH is below the isoelectric point, you have a positive or you have a cation. If it's below the isoelectric point, then the NH2 over here is gains a proton. So what do we have here? What we have is, well, we have an NH3 plus, okay, and then we have a CH3 CO2H. So this is the structural formula. Okay, this is the structural formula of alanine at pH 2. Okay. Alanine exists as a pair of optical isomers. The structure of one optical isomer is shown in figure 5.2. Draw the three-dimensional structure of the other optical isomer of alanine. The other optical isomer will just be the mirror image of this. Okay, so just draw it like that. We have NH2, we have a CO2H, we have an H, and then we have a CH3. Okay. Polymer C forms from the reaction between alanine and 4-aminobutanoic acid. Draw a repeat unit of C. The functional group formed should be displayed. So what you have over here is you have this. You have NH2, okay? You have an NH2 that has 3 CH2s, okay? And then you have a CO2H. That's one of the monomers, right? That's 4-aminobutanoic acid. And alanine over here is this guy, right? Alanine is CCH3, and then you have a H, then you have a CO2H, and you have an NH2. Now, what kind of polymerization do we have here? We have condensation polymerization. So if you guys remember the amide, right? The amide and the carboxyl group over here, the amine and the carboxylic acid group react to form an amide linkage, right? So we have condensation polymerization take place. So what happens is that these guys react, and then the CO2H here reacts with the NH2 here. So the repeat unit would look like this. You have C, CH3, okay, you have an H, and then you have a C double bond O and H, right? That's your amide linkage forming here. And then you have CH2 thrice, and then what you have is you have a C double bond O, right? And then again, this is also forming an amide linkage with this nitrogen over here. Okay, so this is your repeat unit, right? You have a polyamide. You have two different monomers, right? So both of those monomers will be part of the repeat unit here. The type of polymerization here is condensation polymerization. Scientists are investigating C, that's this polymer, okay, as a replacement for polypropylene in packaging. Suggest an advantage of using C instead of polypropylene. Polypropylene is an addition polymer. This is a condensation polymer. What's an advantage of using a condensation polymer instead of an addition polymer, right? Condensation polymers are biodegradable, okay, and they can easily be hydrolyzed. So it is biodegradable. Okay, it is biodegradable. Okay, so it won't stay in the environment for thousands or millions of years. Okay, unlike addition polymers. Okay, a student studies the reaction of 2-chloropropanoic acid with aqueous NH3 to determine the reaction mechanism. The student finds that when 2-chloropropanoic acid and NH3 are added in a 1:1 stoichiometric ratio, the conjugate acid and base of the reactants are quickly formed. Okay, identify the conjugate acid base pairs in reaction 1. So what we have is this guy over here is the acid, okay, CH3, CH, Cl, CO2H is an acid, okay, and the conjugate base of this acid is this guy. The conjugate base is this guy, right? When the acid loses a proton, it makes its conjugate base. So we have CH3, CH, Cl, CO2 minus, okay. And the other conjugate acid base pair that we have is ammonia, which is the base, and when it gains a proton, it makes the ammonium ion. Or we can say when ammonium loses a proton, it makes the NH3. So NH3 is the base and NH4 plus is an acid. So this is the other conjugate acid base pair. So what we have over here is we have NH3, okay, and we have NH4 plus. Okay, this is acid, this is the base, and then NH3 is the base, and NH4 plus is the conjugate acid. In an excess of NH3, the 2-chloropropanoate ion undergoes nucleophilic substitution. Okay, so what's happening here is that the NH3, right, the NH2 is substituting for a Cl over here, and obviously the NH3 is also losing an H plus in the process. The student investigates the rate of reaction 2. The student mixes CH3Cl, COO minus with a large excess of NH3. The graph in figure 5.3 shows the results obtained. Okay, so here we have the graph. Okay, we have a large excess of NH3. Okay, we have a large excess of NH3. That is to ensure that when this guy is reacting with NH3, okay, when this guy is reacting with the NH3 concentration remains relatively constant. Because we're using a large amount of NH3, the NH3 concentration barely changes. So we're only studying the rate with respect to the concentration of this guy, okay, which is the 2-chloropropanoate ion. Use the graph in figure 5.3 to show the reaction is first order with respect to this ion, okay. So we want to show that it's first order with respect to this. So what can we use over here? If you guys remember, what about half-lives can we use? I'll give you a hint, right? The hint over here is half-lives. We know that. So we know that if it's first order, right, it'll have a constant half-life. So here, okay, for example, let's say we take the half-life from this guy here, which is 0.0210, okay, 0.0210. Each square is 0.0010, okay, and we went down to 0.0105, okay, which is this guy over here. What value do we get? We get a half-life of 500 seconds. That's the first half-life, okay, and the second half-life we go from 0.0105 to 0.00525, right? So we go over here, okay, roughly we go to half that concentration, and we get to 1000 seconds. So the first half-life is 500 seconds. The first half-life is 500 seconds, and the second half-life is also 500 seconds. Okay, so we can clearly see that we have a constant half-life, okay, of 500 seconds. Okay, so what we can see over here is that we have a, okay, the T half is 500 seconds, okay, and we have a constant half-life, okay. Therefore, the reaction is first order with respect to the concentration of this ion. Okay. Explain why a large excess of NH3 needs to be used in order to obtain the results. The reason we're using a large excess is so that the concentration of NH3 remains relatively constant, okay. So it doesn't affect the reaction itself, okay. Remains relatively constant, therefore it doesn't affect the rate. All right. The student measures the effect of changing the concentration of NH3 on the rate of the reaction. Table 5.1 shows the results obtained. So what we've done is we've kept the concentration of this anion constant, but what we've done is we multiplied the concentration by a factor of 1.5. Okay, so if you're comparing experiments 1 and 2, okay, what we've done is the NH3 concentration, okay, goes from 0.003 to 0.0045. So it's being multiplied by a factor of 1.5. Okay, and what's happening to the rate? What's happening to the rate over here? Okay, the rate in the second reaction is 2.21 times 10 to the power of -5. Okay, and it's 1.47 times 10 to the power of -5 in the first reaction. Okay, so then the rate is also being multiplied by a factor of 1.5 here. Okay, roughly 1.5 if you take the ratio between the rates. So 1.5 times the concentration of ammonia means 1.5 times the rate. Therefore, we can say it is first order with respect to, okay, the concentration of ammonia as well. Okay. So the reaction is first order with respect to both. Use this information, okay, in table 5.1 and in C part 2 to determine whether the nucleophilic substitution proceeds via an SN1 or an SN2 mechanism. Explain your answer. So the rate of the reaction depends on both. Okay, it depends on both. It depends on the NH3 concentration as well as the, it depends on this concentration as well as this concentration. So they both react, okay. The heterolytic fission and the attack of the nucleophile both take place in the same step. So what type of a reaction is that? Where you have a one-step mechanism, where the concentrations of both, okay, the concentrations of both affect the rate. This would be an SN2 mechanism. Okay, this would be an SN2 mechanism. Okay. The 2 over here comes from the fact that the rate determining step includes both NH3 and this guy. Okay, in the SN1 mechanism, it only depends on the initial reactant and not the nucleophile. Okay, in SN1 it only depends on this, whereas in SN2 the 2 comes from the fact that it depends on the concentration of both. They're both part of the rate equation, hence we have an SN2 mechanism. Okay. Again, the SN2 over here, the 2 comes from the fact that in the rate determining step, both this guy over here and the nucleophile are involved. Okay, if the rate only depended on this reactant and not the nucleophile, if the overall order was 1, then you would have the SN1 mechanism. Okay, if the rate only depended, or the rate equation only had the concentration of this, then it would be SN1. If the rate equation has both, it's first order with respect to this and first order with respect to this, so the rate equation has both of these. Okay, so therefore it's the SN2 mechanism. They're both involved in the rate determining step. Okay, describe the effect of an increase in the temperature on the rate of reaction. Explain your answer. So what would happen to the rate of the reaction if I increase the temperature? The rate of the reaction increases. Okay, and the reason why it increases is because, okay, okay, there are more particles that have energy, okay, greater than or equal to the activation energy, right? This is the Boltzmann distribution, if you guys remember, right? If you increase the temperature, right, the Boltzmann distribution graph over here, right, what you have is, if you had this as your initial graph, right, your graph shift to the right, right? So your number of particles above the activation energy increases, right? And why do more particles have energy greater than the activation energy? It's because, right, you've essentially increased the kinetic energy of the particles, no? The average kinetic energy. So we can say, because you have more particles that have energy greater than the activation energy, we can say therefore we have the frequency of successful or effective collisions increases. Frequency of successful collisions, okay, successful or effective collisions, okay, increases. When an excess of 2-chloropropanoate is used, further substitution can occur. One product has the formula C6H9NO42-. Suggest the structure of C6H9NO42-. Now when this guy reacted with NH3, okay, okay, it formed this. It formed CH3, CH, NH2, okay, this was given in the question, CO2-. And they're saying that if you have more of this present, more of this present, CH3, CH, Cl, CO2-, right, you can have further substitution take place. Now what can happen is that this amine over here, okay, can actually react with this carbon again, because we have an amine over here, right? You can have further substitution take place to go from a 3-carbon product to a 6-carbon product. So how will that further substitution take place, right? This guy will react with this to form, okay, I'll draw this out in a bit more detail. Okay, what we have is this. We have CH3, okay, then we have C, H, NH2, okay, CO2-, and then we have CH3, C, H, Cl, and CO2-. And we have further nucleophilic substitution take place. So what happens is that this amine reacts with this carbon here, okay, and this CCl bond breaks. That's why you have further substitution taking place over here. Okay, so what do you end up making? You end up making this. Okay, I'll draw the structure. You have a CH3, you have a C with an H, and now this nitrogen bonds to this carbon. This nitrogen bonds to this carbon. Okay, so this nitrogen over here ends up bonding to this carbon. Okay, this nitrogen over here ends up bonding to this carbon, and this carbon is bonded to an H. This carbon is bonded to an H. It's bonded to a CO2 minus. Okay, and it's bonded to a CH3. Right, and now nitrogen obviously will have 3 bonds, so we'll also have an NH over here. Okay, similar to what happened in the previous reaction. Okay, what happened in this reaction was NH3, when it reacted with this carbon and the nitrogen formed a bond, and the NH3 lost a proton. Right, the same thing is happening here. But now instead of ammonia you have an amine. Okay, instead of ammonia you have an amine. So this nitrogen is losing a proton, it's becoming an NH, okay, and it's reacting, bonding with this carbon, and obviously it's substituting for the halogen over here. Okay, so this is your product. This is your product over here, right? Here obviously I haven't shown the CO2 minus. Okay, I haven't shown the CO2 minus over here. I'll show it a little more clearly, okay, just so that we have a little more space over here. Okay, what you have is this. You have a nitrogen, okay, that has an H, and this nitrogen is bonded to this carbon. This carbon has a CO2 minus, a CH3, and an H. Has a CO2 minus, a CH3, and an H. Okay, this is your product here. Okay, you can show it as a skeletal formula, you can show it like this, it doesn't matter how you show it, all right? But this is your answer. The idea here is this: when you have an NH3, right, and you have a CCl bond, what happens is the nitrogen bonds to this guy, right, and you end up making something like this. You end up making CnH2, right, and obviously the NH3 loses the proton and it loses the Cl minus. This was given to us in the question. Right? So what happens here is this, that now instead of an NH2, what you have is this. Right? Instead of an NH3, sorry, instead of an ammonia that you're starting with, you have something like RNH2, right? Your entire R group over here is the CH3, CH3, CO2 minus. This entire thing is your R group, right? When this reacts with a CCl bond, okay, when this reacts with a CCl, with a halogenoalkane, again, the same thing happens, right? And what ends up happening is you end up making this guy. The NH2 loses a proton, right? So you end up making CNHR, okay, plus H plus Cl minus. Okay, so what you have over here is this. Okay, right? What you have is you have this NH2 with an R group. And this N over here is substituting for the chlorine. So you end up making C with an NHR. Okay, that is this guy. Okay, C with this NHR, this entire thing over here. Okay, and then the initial compound with the chlorine, right? The initial compound with the chlorine also had this thing bonded to it. Okay, so that's how you're supposed to understand it. All right, this nitrogen over here, okay, has bonded to this carbon over here. Okay, this carbon was initially bonded to the chlorine, and this nitrogen obviously was initially an NH2. All right, so that was the reaction that's taking place here. Okay, all right. So here we have question number 6. Okay, which says lidocaine is used as an anesthetic. A synthesis of lidocaine is shown in figure 6.1. Okay, so here's the figure, right? Here we have lidocaine as our product. Okay, and we're starting with these two materials. We have this phenylamine with this type of the certain phenylamine over here. Okay, where we have 1,6 or 2,6-dimethyl phenylamine, and we have this acyl chloride. Okay, now W can be formed by reacting this guy over here. Okay, this is hydroxyethanoic acid with an excess of SOCl2. Okay, so what we're doing is we're essentially converting this compound. Okay, we're converting this compound over here, okay, to this compound. So we're substituting both the OH groups with a Cl. Okay, so what we have over here is we can use PCl5 or SOCl2 over here. We can use PCl5 or SOCl2 over here. And what do we get here? What we get is this. We have CH2, right, OH, and then CO2H reacting with SOCl2, okay, reacting with SOCl2 to form, okay, reacting with SOCl2 to form this. Okay, what do we get here? What we get is we get Cl, okay, CH2, COCl, right? So what's happened over here is that the two chlorine atoms have substituted for the two OH groups over here. Okay, the two chlorine atoms have substituted for the two OH groups over here. So what we're left with over here is we're left with two OHs. Okay, we're left with two OHs over here in the balancing of this equation. We're left with two OHs, and we're left with an S and an O, right, from the SOCl2. So what do we end up making? Well, what we end up making over here is SO2 and H2O. Okay, we end up making SO2 and H2O. We know that sulfur has an oxidation number of +4 here, so it'll have an oxidation number of +4 in the product. So we know that we're making SO2. Okay, and then we're left with H2O. Okay, we're left with H2O if you balance this equation. All right, so this is how you can construct this equation over here. After W and X have reacted together, an excess of the ethanoate or sodium ethanoate is added to the reaction mixture. Suggest why. Okay, so why are we adding sodium ethanoate after W and X have reacted? Okay, after W and X have reacted, what we're getting here is a condensation reaction, right? We're making an amide between the amine, the phenylamine, and the acyl chloride, but we're adding sodium ethanoate right after. Why are we doing that? The reason we're doing that over here is because in this reaction we're also making HCl. In this reaction we're also making HCl, right? We have a condensation reaction between an amine and an acyl chloride. And what this guy does is, okay, what this guy does over here is, this is sodium ethanoate. The ethanoate ion over here is a base. Okay, the ethanoate ion is a base. So we have to suggest why we're adding a base. The base is neutralizing the excess HCl produced. Okay, so neutralizing the HCl produced. Okay, neutralizes the HCl produced in the first reaction, okay, between W and X. Again, we don't need to know why we need to do that. You just need to suggest why you're doing it. Okay. The reaction of W and X, reaction 1 follows an addition-elimination mechanism. Complete the mechanism for the reaction of W with X. Include all relevant curly arrows, lone pairs of electrons, charges, and partial charges. Use ArNH2 to represent X. Okay. So we have W and we have X. Okay. And what happens is an addition-elimination, right, between an acyl chloride and an amine is this happens, right? What happens is that this guy, okay, what you have is you have an acyl chloride here, so you have a delta plus, okay, and you have a delta minus, right? And what happens is that this NH2 attacks this carbon, okay, and this bond breaks. This bond breaks over here, and what you end up making over here is this. Okay, you have an NH2, right? You have an NH2 with an AR, right? And then you have a Cl here, and you have a CH2 Cl over here, right? This carbon is bonded to a Cl and a CH2 Cl. Now, we know that in this reaction, we're getting rid of this chlorine, right? But what we're making is HCl in this reaction. So how do we make the H, right? What we have is in the product, if you notice, right? What you have in the product is instead of an NH2, you have an NH. You have an NH over here instead of an NH2. And you also lose this chlorine. That's how you get the HCl. So we have to show that clearly in our mechanism. So if we complete the mechanism here, right, we have to show the formation of HCl as well. And the HCl forms because this guy loses a proton like this, okay, and the Cl is also removed. Okay, so you have a delta minus Cl and you have a delta plus carbon here, and that the pi bond between the oxygen and the carbon atom is reformed. Okay, so the chlorine atom leaves. Okay, the pi bond is reformed, so the electrons go back to form the pi bond, and the hydrogen atom also leaves over here. Okay, so what you end up making is your final product over here is this. You have C double bond O, you have a CH2Cl, you have a CH2Cl, and you have the NHAr. Okay, that's this guy over here. Okay, and you obviously make HCl. All right. C2H5 twice NH reacts with Y in reaction 2. Explain why it can act as a nucleophile. Why can this guy act as a nucleophile? Okay, in reaction 2, what happens is they're saying this amine, okay, this amine can act as a nucleophile. This amine can act as a nucleophile and substitute for the chlorine atom here. So again, this is nucleophilic substitution, right? You have a halogenoalkane group here that is being substituted for by an amine. It can act as a nucleophile because it has a lone pair of electrons to donate, okay, on the nitrogen atom. Remember, nucleophiles are species that donate lone pairs of electrons, okay? So here we can say that it has a, okay, the nitrogen atom, okay, has a lone pair of electrons, that it can donate. Okay, that's a nucleophile to form a dative bond. Okay. All right. The purity of lidocaine can be checked using thin layer chromatography. Ethyl ethanoate is used as a solvent. The RF values of X and lidocaine are given in the table. Identify the substances used as the mobile and stationary phase in this thin layer chromatography experiment. Okay. Now, the mobile phase over here is your solvent. Okay, in this thin layer chromatography, okay, the mobile phase that you're using is your solvent, right? The solvent that you're using over here is ethyl ethanoate. So that is your mobile phase. Okay. And the stationary phase is whatever the plate is coated with. Okay, the plate is usually coated with a solid and it's usually SiO2 or Al2O3. So you can say SiO2 or you can say Al2O3. Suggest how the RF value can be calculated. The RF value, okay, the RF value is simply the distance traveled by the component, right? Okay, by a substance. Okay, by a substance divided by the distance traveled by solvent front. Distance traveled by solvent front. Okay, that's how you calculate the RF value. Suggest why the RF value of X is less than that for lidocaine. Okay, now they're saying essentially if the RF value is lesser, so let's say this is your solvent front. Okay, this is your solvent front and this is your baseline. That's your starting point, right? That's what you draw with a pencil. And they're saying that X, okay, X travels a shorter distance than lidocaine. X travels a shorter distance than lidocaine. Now, there could be two reasons why the RF value is smaller. Remember, the distance traveled by the substance X is lesser than the distance traveled by the lidocaine because lidocaine has a greater RF value. Now, X travels a shorter distance for two reasons. One reason could be that it's not as soluble in the solvent, so it doesn't go with the solvent as much. The other reason could be that it adsorbs to the surface more strongly. In other words, जो हम लोग SiO2, the SiO2 or Al2O3 that we're using, okay, as our stationary phase, X could bind more strongly with it and therefore not go a further distance, therefore travel a lesser distance. So there's two reasons why the RF value for X is lesser. We can either say that X is adsorbed more strongly to the stationary phase, okay, to the stationary phase, or you could say that it is not as soluble, okay, it is not as soluble, okay, X is not as soluble in the mobile phase or in the solvent. All right. The proton NMR spectrum of lidocaine is shown in figure 6.2. Okay, so here's the proton NMR spectrum, right? We have this table that shows the proton NMR spectrum values, all right? The question is asking, name the splitting pattern at 2.6 and 1.1. So at 2.6 and 1.1, what's the splitting pattern? At 1.1, the splitting pattern is a triplet, right? We see 3 peaks. And at 2.6, it is a quartet. Okay. Yeah, always Al2O3 or SiO2 will be used as a stationary phase, one of the two. Okay, those are the most common ones. Okay, so 1.1 is a triplet and 2.6 is a quartet. Okay, so 1.1 is a triplet. Okay, and 2.6 is a quartet. The relative peak areas at 3.0 and 2.3 is 1:3 respectively. Identify the protons in the NMR spectrum of lidocaine that are responsible for the peaks at the following chemical shift values. Okay, so 7.1, 3.0 and 2.3. So at 7.1, okay, at 7.1, what is the kind of proton responsible for the shift at 7.1? Okay, the range of around 6 to 9 is when you have a hydrogen bonded to a benzene ring, right? So here what you have is you have these 3 hydrogen atoms here directly bonded to the benzene ring. They'll give you a shift of around 7.1. You don't need to know why it's a multiplet. Okay, the splitting patterns for benzene aren't taught in our syllabus, but you can have a multiplet as well. It doesn't have to be a singlet, but all of these protons are the protons on the benzene ring. Okay, so this type of a proton is a proton that's attached to an aromatic ring. So 7.1 is a proton attached to an aromatic ring. It is a proton attached to an aromatic ring. Okay, attached to aromatic ring. Okay, this is given in the table. The description is given in the table, right? Now, the next part of, they're also saying they want to know, the question also says that the ratio between 3.0 and 2.3 is 1:3. Okay, now the proton that was at 7.1 was obviously, as we just said, it was attached to an aromatic ring, right? HAR. Now, what we have over here is, what's the proton at 2.3 and 3.0? Let's see. Okay, let's look at the structure of the molecule as well at the same time. Okay, let's look at the structure of the molecule at the same time. Okay, at 2.3 and 3.0, in both cases we see a singlet. In both cases we see a singlet, right? So, and we know, again, the question says that at 3.0, okay, the peak is 3 times shorter. 2.3 wali peak is 3 times taller over here. Okay, the 2.3 peak is, the area is 3 times as much. Sorry, not height. The area is 3 times as much for the peak at 2.3. Now, in the 2, so we have to figure out 2.3, okay, which is 3 ka ratio, and 3.0, which is the height is, or the relative area is 1. So at 2.3 we can have two things. Either we have it directly bonded to the aromatic ring, right, or we have it alkyl next to the C double bond O, right? Now, next to the C double bond O, we have 2 protons, okay, whereas for the alkyl next to the aromatic ring we have 6 protons. So which one is the one bonded to the aromatic ring? It has 6 protons to the aromatic ring, 2 protons next to the C double bond O. So this one, let's say the one that has a height 3 times taller, or the area is 3 times as much, is this bonded to the ring, or is it bonded to the C double bond O? This guy over here. This height is 3 times as much. Is it the 6 protons or the 2 protons? It must be the 6 protons, right? So the peak at 2.3, is the alkyl next to the aromatic ring. Okay, the 2.3 is the alkyl next to the aromatic ring. Okay, alkyl next to aromatic ring, right? And 3.0 is the alkyl next to the C double bond O. Predict the number of peaks present in the carbon-13 NMR spectrum of lidocaine. Okay, so we want to know how many different types of carbon atoms are present in this molecule, right? Now what we have is we have a line of symmetry here, right? We have a line of symmetry over here, right here, right? So we can say that this is one type, right? This is one type. These two are identical. These two are identical, right? These two methyl groups are also identical. That's 4. Then you have this guy, which is the fifth one, right? 5. Then this guy, which is 6. Then 7. And then you have 2 ethyl groups which are identical. So each of those ethyl groups have a total of 2 carbon atoms that are non-identical. And both the ethyl groups are identical. Okay, both the ethyl groups are identical. So these two are the same, and these two are also the same. So we have 7 plus 2, which is 9. So we have a total of 9 different carbon 13, or 9 different peaks in the carbon 13 NMR spectrum.